Section 2.10, Bond Properties. First, bond order. It's very simple. You count the number of bonding electrons. You count the number of antibonding electrons. Take the difference. And then divide the difference by 2. Therefore, lithium, 2 bonding electrons, 0 antibonding electrons. Bond order is 1. Beryllium, 2 bonding, 2 antibonding, 0 bond order. Now let's look at boron 2. Now, this time, ignore this 1 sigma G and 1 sigma U because they cancel. 2 bonding electrons, you have a single bond. Carbon 2. Ignore this, you have 4 bonding electrons, the bond order is 2. Nitrogen. Well, ignore this, you have 6 bonding electrons, the bond order is 3. Ignore this for oxygen, you have 6 bonding electrons, 2 antibonding electrons, and then the bond order is 2. Just remember, these 2 electrons each occupy a pi orbital, and they have the same spin. Therefore, oxygen is a triplet. Now, fluorine. Well, 6 bonding electrons, 4 antibonding electrons. The bond order is 1. Now, I'm going to ask you a few more questions. What about the bond order of carbon 2 minus, nitrogen 2 plus, nitrogen 2 minus, oxygen 2 plus? If your answer is 2.5 to all 4 questions, you are correct. Carbon 2 minus, you just put 1 more electron here. You have 3 bonding electrons. Oh, I'm sorry, you put 1 electron here. You have 5 bonding electrons. That's carbon 2 minus. You have 5 bonding electrons in total, 0 antibonding electrons. Nitrogen 2 plus, you just remove 1 electron from here. Again, 5 bonding electrons, 0 antibonding electrons. So the bond order is 2.5. Nitrogen 2 minus, that means you have 6 bonding electrons here and 1 antibonding. The bond order is 2.5. Oxygen 2 plus, you delete this one, and then you have 6 bonding, 1 antibonding. Well, the difference is 5. The bond order is 2.5. What if I add 1 more electron here? Now you have 3 antibonding electrons, and then 6 minus 3, that's 3 divided by 2. The bond order is 1.5. Fluorine 2 plus, get rid of 1 of the electrons, and then you have 6 bonding, 3 antibonding. So in F2 plus, the bond is stronger than in F2. More bond properties. If you have a larger bond order, you have a larger bond energy. So bond order here, this is nitrogen-nitrogen single bond, oxygen-oxygen single bond. How do you make this? I think you can just look at hydrogen peroxide, and this one could be NH2, NH2. These are single bond. So those are single bonds, different single bonds. Double bonds here, triple bond here, and this is 1.5. You can find this in a conjugated system. For example, benzene, I think the bond order is 1.5 here. And then you look at the bond energy, you have from 1, 2, 3, you have higher and higher bond energy. And also, the bond order can be used to predict the bond distance. Not very accurate, but here's the trend. Single bond is longer than double bond, which is longer than triple bond. Especially if you're talking about the same, 2 atoms. CC double bond is triple bond, CC double bond, CC triple bond, single bond, triple bond, single, double, triple. It's almost linear. And then let's look at some other cases. Let's look at CO, and O. There's no CO. So, but anyway, CN. So it's good. Anyway, the higher the bond order, the shorter the bond distance. Again, I mean it's not very accurate here or here. It just tells you a way to determine the ranking of bond energy and bond distance. More qualitatively, a triple bond is stronger than a double bond. A double bond is stronger than a single bond. Therefore, the bond energy of a triple bond is greater than the bond energy of a double bond. The bond energy of a double bond is greater than that of a single bond. The triple bond distance is shorter than the double bond distance. The double bond distance is shorter than a single bond. And then, of course, if the bond order can be used to determine this bond distance and bond energy, and of course we can plot this bond energy versus bond distance. When you have a shorter bond, there's going to be more bond energy. When you have a longer bond, there's less bond energy. That's just a qualitative analysis here.